In this last example, example H here, we saw an alternating sequence that was alternating between these yellow highlighted values that were less than 1 and these green highlighted values that were greater than 1. But both the yellow and the green values approached 1. So because they were both approaching 1, we would say the entire limit equals 1. This next example, example I, looks pretty similar, and when in doubt you can expand it out, or we can notice the big difference here is a multiplication, right? We're multiplying by -1 to the n, where n is going from odds to evens, back to odds, back to evens, back to odds, back to evens. So this piece right here is going to alternate between +1 and -1. And we are multiplying that, not adding it in this case, but multiplying it by this thing, n minus 1 over n. Now, n minus 1 over n is going to approach 1 as n goes to infinity. Approaches 1 as n goes to infinity. So this series is going to look an awful lot like, a sub n is going to look an awful lot like the sequence -1, +1, -1, +1, etc. Eventually, right? Once n gets big enough, these terms are going to be extremely close to +1 and -1. And we've already talked about what happens when our sequence does not approach a single value. In this case, it's approaching two distinct values. We would say that this sequence diverges by oscillation. So the key difference here is that example H is alternating between higher than and lower than a single value, namely 1, whereas this example, this sequence I, is oscillating between two distinct values. So make sure you make that distinction between those two types of sequences. All right, moving on. We've got example J has an exponential on the top and a factorial on the bottom. So just referring to our hierarchy of infinities here, exponential grows to infinity, but not as fast as factorials. So we would expect this to be 0. And in fact, it is. We can kind of play around with this a little bit and verify. For example, first of all, notice that it's n on the top and n plus 1 on the bottom. That's just going to be an extra piece that's going to push this to 0 faster, right? Because if we consider 2 to the n over n plus 1 factorial, we know that n plus 1 factorial is the same thing as n plus 1 times n factorial. Lo and behold, now we're comparing apples to apples because these both have n. Not only that, but this n plus 1 makes this fraction even smaller. You can play around with numbers to try to convince yourself further, or you can think about what if n is very large. For example, let's say 100. We're going to have 2 times 2 times 2, 100 times. And on the bottom, we're going to have 101 that doesn't really get paired up with anything. And then this 100 that gets paired up with this 2, and this 99 that gets paired up with this 2, and this 98, which gets paired up with this 2, all the way down to, well, let's have a 2 that gets paired up with this 2, and a 1. So we can think about this as a whole bunch of fractions. 2 over 100 is less than 1. 2 over 99 is less than 1. 2 over 98 is less than 1. We've got about 100 numbers here, all less than 1 that we're multiplying together. Every time you multiply by a number less than 1, you're shrinking the value. We do have this one annoying 2 over 1, which is bigger than 1, so that's going to make it grow a little bit, but compared to the other ones, is not going to be significant enough. So this is not a mathematically formal proof. It's kind of a loosey-goosey sort of well, because factorial grows faster than exponential, then we're going to go ahead and say that this goes to 0. And for the sake of this class, I'll accept that. If you want a more mathematically rigorous proof that the limit of this sequence is 0, therefore the sequence converges to 0, then I recommend you look into a concept called mathematical induction. And we can prove this using mathematical induction. Not something that you need to know for this class, but is useful for many of these concepts. All right, K should look familiar. We've seen this one before. We saw this one back in Chapter 8 when we were learning about L'Hopital's rule and indeterminate forms. The limit as n approaches infinity of 1 plus 1 over n raised to the n. I hope we recognize this by now to be defined as e. Therefore, the sequence converges to e. Converges to e. You can go through the process of proving that by taking the natural log of both sides and using properties of logs and all that stuff. But we've seen this a number of times, and I don't need to reinvent the wheel at this point. All right, L. L has factorial on the top and really, really big exponential. It's like doubly exponential on the bottom, right? The base and the exponent are increasing. So if we look at our hierarchy of infinities, n to the n is the largest we've got. So clearly, if we put n to the n on the bottom, this is going to approach 0. But wait, that's if we're comparing apples to apples, right? If we have n factorial on the top and n to the n on the bottom, then yes, this would approach 0. But this is not n on the top. This is 2n on the top. So the question now becomes, does that make the top bigger enough so that it beats the denominator? So does this go to 0? Does it go to infinity? What does it do? And again, this is another one where induction might come in handy. Or we can think about this with the first few terms, and maybe that will kind of help us along. When n equals 1, we have 2 factorial over 1. When n equals 2, we have 4 factorial over 2 to the 2, which is 4. When n equals 3, we're going to have 6 factorial on the top, which is 720, over 3 to the 3, which is 27 on the bottom. Now, both of these numerator and denominator are both growing, but the numerator is growing so much faster than the denominator. Now, again, that's not very mathematical, so much, right? But here's another way we can think about this. If we think about 2n factorial as 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 times 2n minus 4 times 2, all the way down to n, eventually we'll get down to n. I'll say n plus 1, and then I'll say n. And then I'll get n minus 1, and I'll get n minus 2, and I'm going to keep on going until I get down to 1. So these first terms, these first factors, I should say, there are n of them. There are n of them in n factors in this first half of the list. And there are another n factors in this half of the list, n more factors. That's the numerator. And then when we consider the denominator, we don't have 2n factors, we only have n factors. So if I match these up, I'm going to put an n here, and an n here, and an n here, and an n here, and then I'm out of n's. Each one of these fractions is greater than 1, because the numerator of each of these is bigger than n. So bigger than 1 times bigger than 1 times bigger than 1, this thing is growing. And then we still have all these extra factors that are going to make this product grow even bigger. So this definitely diverges to infinity. Again, not a mathematically rigorous proof, but for the sake of this course, I would accept that.